Oh, okay. All right. Um, Actually, the wireless communication needs some signal to be used as a carrier of your data. It's not only the electrical signal, but it is also electromagnetic signals. As you look at the slide title, if you have an electrical engineering background, that you may know that there is a magnetic field as far as there is electric fields, right? That's all coexistence. Um, that is a part of the techniques that we maximize our fundamental theory for wireless communication is electromagnetic signals. Electromagnetic signal is a function of time, right? If you see electromagnetic signal can be also expressed as a function of a frequency. So, um, so as we looked at, we can analyze the signals over the time axis. The same way we can analyze the signal over the frequency axis. You can count per second how many occurrences. When I say some, as you reported on your smartphone or CNN, then there's some, depending upon the pitch of my sound, acoustic, you may say, oh, this type of signal patterns occurs more often than some others. Right? Not just simply, hey, time x, you have this magnitude, time x plus 1, you have another, and time x plus 2, and another, and there's time domain analysis of speech. Similarly, we can do the same source of the signal over the frequencies by saying this type of occurs, this type of frequency pattern occurs, for example, million times. Another pattern occurs half a million. Another pattern, some of the number. Okay. So we will look at two different domains to analyze frequencies or signals, not as actually frequencies, signals, right? Waves, that's what we are talking about. If we say wave or signal, there are basically two types of signals, right? Analog and digital. You all know what I mean by that, right? Analog, our voice, acoustic signals are all analog signals. Signals from computer, this is digital, right? Even if it's digital usually 1 or 0, right? That's too simple. 1 or 0. But in real digital signal, not only one, well actually 1 or 0, but step, there's some step, right? But it's not necessarily step up and step down, step up, step down, which means two levels. It's so simple. Our digital wireless communication is not necessarily using, it's not, yeah, it's not carrying over only two levels of digital signals. There's much different levels, right? You can start. For example, think about the voltages. 1 volt, 2 volts, 3 volts. Depending upon the something here. If I can do, for example, not necessarily up, down, 1 over 0, right? Let's say this is 0 or this is 1. It's not necessarily high upper bound is 1 and lower bound is 0. But depending upon our interpretation, right? We could do something different. Let's say this is a positive 5 volt. LT and negative 5. Or some other, we're talking about digital signal, right? In some other cases, we may do 5 volts, 10 volts, 15 volts, 20 volts, 25, and drop some, something like this. That may be possible, right? In that way, we can distinguish the code more efficiently. On the other hand, the analog signals, like our voice signals, it fluctuates, something like this, over the course of the time. Still, there is a time, right? So basically, two types of signals. If we look at this analog or digital, as we analyze it, we may be able to see if there is some period, some repetitions. And we call that periodic signals, which means the current, we have some signal at time t, right? So time elapsed a little further, capital T. So now time is t plus capital T. The signal, the characteristics of a signal, this function, s of something, so s of t plus capital T is the same as s of small t, which means current signal is the same as the signal that we saw before, right? If we keep having that repetition, then we call it periodic signals. If it is not, then aperiodic. So for those, we could say that for analog signal and digital signal also, there's a periodic digital signal, aperiodic digital signal. Same thing for analog. This is a typical analog signals, right? This is a typical digital signal. We have only two levels. Okay. If you have a device to generate two-level digital signals, then very easily you can have two different voltages, 5 volts or no voltage, or positive 5 and negative 5. And there's a amplitude. All the signals, we have amplitude. And therefore, we can think of a peak amplitude. In our previous example here, the peak is here, right? This is a peak. And frequency now. What is the frequency? Frequency is the rate. at which the signal repeats. The unit that we usually use is hertz, right? Which is a French name. Some mathematicians multiple years ago in France. I don't know, was France at the time? Which one? And there is a French. I see. So, somewhere he found that terminologies. But we still use that. Physicist? Right. Okay. Now, there's some terminologies that we need to define. First of all, period. Period is amount of time it takes for one repetition of a signal. So any signals, it starts from here and it ends here. So this is one pattern. It keep repeating. So we call this is period. So period of latency of all usually for this 560 course is 10 minutes. Then there's a period, right? And another 10 minutes we have a lecture coming in. Period is correlated with the frequency. F, there is a frequency. If we have a long period, then for time beat, you have smaller. If period is very, very short, it repeats very quickly, then for time minutes, we have more occurrences. So that is what this equation tells us, right? Are really opposites. Phase. Phase is a measure of the relative positions in time. So some signals starts from here, but another signal starts from, let's say, here. Exact same signal, but there is some shift. So this is a phase. Wavelength. Wavelength is the distance of the single cycle of the signals. So from here to there, that is wavelength. You can measure at any point. What is a wavelength? Then we can say, oh, from here to there. Then this wavelength is the same as that wavelength and that wavelength. They're all wavelengths. By having this period, frequency, wavelength, and by borrowing the speed issue of light, what is light speed? Light speed is 3 times 10 to the power 8 meter per second. It may not be clear to Americans, right? Because it says meter. 1 meter means 3 feet, right? So if you multiply this speed by 3, then that is bit approximately, right? Is that right? Maybe so, right? Yeah. So there is a formula among three parameters: wavelength, frequency, and speed, velocity. Then lambda f equals v. So lambda equals lambda here. If we divide by f both, then lambda equals v over f, right? Which is the same as v times 1 over f. And 1 over f is nothing but here. Therefore, we say this is t. So v times t here. As I said, try not to wear my glasses. Eventually, I think I went to eye doctor last Friday. He said I have had the eyes to go for so many decades. So now try not to, so that my eyes will be better in the future. Frequency now, finally we are thinking of frequency. As we looked at, frequency can be obtained by this formula if we agree this, right? Lambda equals v times 1 over f. In other words, from here, if we divide both sides by lambda, then lambda canceled out, and f equals v over lambda, which is here, v over lambda. That's a frequency. So what is the frequency? This is a formula that we can obtain, right? We can calculate it from this is the speed of light speed. This is a wavelength. So as far as there is a light speed signals, and as far as we know the light wavelength, then we can calculate frequency. So frequency is the number of occurrences per unit time. But if we calculate the hertz number in hertz, then time unit is always second. So how many occurrences per second can be denoted as a frequency? So, for example, light speed is 3 times 10 to the power 8 meter per second for the wavelength given in the table on the next slide, which is here. If you look at here, then we see all the wavelength here. There's some other symbols here. A, and then there is some circle on top. So look at here, 8,000 something, 7,000, which is near infrared. So our radio wave is somewhere far below here. Sorry. And these are all visible color spectrums. So we have red here to all the way up to violet.
The difference between red and violet in wavelength is this, about 7,000, we call that angstrom. Angstrom. It's a French, right? It's Swedish? I'm sorry. I need to drink some coffee because I do not have water. 4,000. Oh, wait a minute. Is it 4,000? Maybe here. Yeah. Yeah, a little bit. 4,000 angstrom. Angstrom. About 3,000 angstrom difference. There's a wavelength. So the length of the cycle of the frequency of the signals is that long, right? 3,000 angstrom long. Is it really long? Back here. How long is it? If we have 3,000 angstrom difference, then 3,000 times 10 to the negative 10 meter, 3,000, therefore 3 times 10 to the negative 7 meter, meter and millimeter, micrometer. Millimeter is a 100 meter. What is a power negative 3? Is a micrometer, and then another negative 3. So anyway, this is a very, very short distance. So when you see red color, some red color and red here, oh, they took my books here from my bookshelves. No one will read this book except me. And Andrew here, these two books. Yeah, these two books from my bookshelves. Anyway, this red and violet, some of you like it? No. But anyway, we don't see any wavelength difference when you see it, right? Wavelength is that we cannot see the difference at all. That's micro and yeah. Nano, yeah. Okay. So what I want you to do using this formula, I want to ask you to calculate the frequency of blue light. Blue light. So if you see here blue light, where is blue light? Blue light here, what is the wavelength of blue light? 4,500. Let's say 4,500. 4,500 angstrom. Take it to 4,500 times 10 to the power negative 10 meter. Plug this to this. We have a meter here. Don't convert that to another unit because we have the same unit here, meter and meter, right? And they maybe canceled out, this meter and meter together. And what's left is per second. If we have a per second, then that is the frequency, right? How many times of occurrences per second. So that is the frequency. So we can see it quickly, right? So according to this, what happens? 3 times 10 to the power 8 meter per second, and here the wavelength is 4.5 4500, so 4.5 to the power 3 times, we need to use this, right? 10 to the power negative 7 meter. So so meter and meter canceled out, and what's left here is per second, and here 10 to the power 3 and negative 7. If we cancel the negative 7 here, then negative 4, right? Negative 4 will be 10 to the power 12 together this, and 3 divided by 4.5 means, I think, point let's say point 7, then 0.7 times 10 to the power 12 hertz. Gigahertz is 10 to the power 9, right? And giga and terahertz is 10 to the power 12. So what is the frequency of blue? Blue is
almost 0.7 terahertz. So blue light high frequency. Then the frequency that we use for our cell phone. Cell phone is only gigahertz, 2.5 to the power 25 gigahertz. Blue light, and of course the light. Shorter wavelength, therefore higher frequency. If we have higher frequencies means what? In general, that's the high frequency. We have data. So for one cycle, I want to put one data. If I send, for example, mercy, MERCY, over no frequency, carrier frequency, we have fluctuations. So one cycle, I want to put M, next cycle E, next cycle R, next cycle C, next Y. So mercy will push it up. So more data can be sent if we have a higher frequency, right? In general. But that's not that simple. Okay, good. Understand a little bit? So that is important. The fundamental. For securities, then, oh, no, we do not want to put n on only one cycle. Let me move that out. So we have 16 cycles, and I want to put n and m and n in the system. Next is 16 e, b, d, e, e. Next, y is so less likely use data.
if you see this, then this is alpha hertz. I do not know what alpha hertz is. So blue is somehow is a hertz, octave. I don't know. somehow this is audio hertz or hertz. Some others. Okay, so here's a little bit of summaries. Low frequency, low wavelength to high, low wavelength to higher wavelength, almost zero wavelength to Planck's length. So wavelength is
almost zero. Armstrong is maybe 10 meters, right? Armstrong. So usually we don't say 0.1 Armstrong. Zero is
And if we have a low wavelength, then there is almost a high frequency. So correspondingly, to higher wavelength, then there is a low frequency. So look at this table. Radio frequency wavelength is 0.1 meter. So 10 centimeter, right? 10 centimeter. Meter. Meter is this big, this wide, right? 0.1, then 1/10. Pamela, how wide is 0.1 meter? 10 centimeter is this? About this? No, two difference. Look at the Abu Pamela. Who is right?
so
Radio wave is 10.
so like this.
Frequency is 3 gigahertz.
3 gigahertz. 3 times 10 to the power 9 meters. Right? 3 gigahertz. So radio wave usually our radio signal 24 gigahertz.
Makes sense. Microwave 2.2 times
2 times 10, 2 times
10 to the power hertz to 3 times 10 to the power 12. So 2.4 gigahertz.
which is very widely used these days. That is microwave or radio frequency. Radio wave or microwave frequency. That frequency that our cell phone, smartphone, Wi-Fi, all are in that band,
Frequency band. So microwave is 3 times 10 to the 12, which is 3 terahertz. So look at here. There is a radio wave, wavelength in meter. Oh, this is greater than that. So let's say 1 meter. Radio is more than, this is a 1, right? So more than 1, somewhere from here, according to this table. So that is a radio wave. Microwave, 0.1 to 10 to the negative 4. Microwave, this picture is a little, that's not exactly matched, but microwave is somewhere here to all the way somewhere here. There's a microwave. It's not really accurately aligned with this table, but actually somewhere like that. Waves, signals does not exist because we first formulate like that, right?
it existed before we formulated. Signal existed. Therefore, we measure it and develop some theory. So finally, we do that. That's what initially the first. That's how what is the approach of this test. approximately. Look at this. This is not really accurate. This is not really accurate, but somehow they are related in this way. X-ray here 10 to the power 9 somewhere. It should be shifted a little bit. This in meter. That is also in meter. Yeah, gamma over there. But bottom line here is that if we have that speed and some wave in that speed, and if we know the wavelength, then you can see frequency. The way that we can see frequency is because we count. No, can you count? This is just a formal language.
Okay. The picture for the same wavelength, I mean waves, signals, is in this way. Petahertz, petahertz, terahertz, gigahertz, and kilohertz, and hertz. So radio frequency is here somewhere, right? Which is gig. Microwave here. So this is what we are going to play for Wi-Fi and cellular signals. And X-ray here, gamma. From
Doing some of it. There's a first picture arrived from it was the picture was taken out of finally arrived at Vietnam. I don't know the exact number, but just yeah, maybe years ago, there and we traversed from that end toward it took
depending upon this frequency, we have we may feel some temperature, right? Here, sunlight's indivisible. Oh no, ultraviolet. This is not visible. Or infrared, yes, only here visible, so that we can see the lights, right? Hot, cooler, warmer here.
why that happens because there's atoms on so
We can say the temperature there. Some TVs, mobile communications somewhere here, But actually now it moves to the cell communication is somewhere here, 2 to the power, 2.4 gigahertz, cell and PCS. TV sets here, VHF, HF in this range, and our radio, AM and FM, is in this hertz, some kilohertz, right? AM, AM is kilohertz, FM megahertz, right? So FM is higher frequency than AM in our radio broadcasting. I think it comes through wire carrier, right? It's not wireless. So there is a Ethernet. Oh, there is also wireless. And it carry over satellite signal, right? The satellite dishes, right? Then there is somewhere here. So these satellite dishes here, microwave, so some gigahertz. So higher frequency. Maybe therefore then from here to that direction. So from low frequency to higher frequency. So we can expect, for example, like hundreds of years later, then our uh, smartphone communication may be over X-ray, X-ray frequency. So that it covers and really high speed, right? Somewhere here. Some even terahertz or petahertz, then it's really high frequency. That may be possible later. And also you can see here the frequency in pictorial, right? This is very, very high frequency, as you can see here. This is a low frequency. Therefore, we have a longer wavelength from here there. Wavelength here is very short. Wavelength from here there, right? That is the wavelength. Any comments? So that explains to you by looking at that okay, more theory, in more mathematical forms. We can think of a typical sine signal, sine wave, to depict the signals like this. Usually the form of a sine wave is in this way. This is general form. Sine, and then there is some shift. This is called phase, right? If there is no phase, then 0. So there is no second term. In the argument of the sine function is 2 pi f. If you see here f and t, then the signal can be formed over frequency and time. There's a frequency portion and time portion. and 2 pi is nothing but 360 degree. So what you can see here is very similar to like a circle. I have this card. I downloaded this. You can download also. I want to share with you some of the frequency generator program. This currently, this noise is 1000 hertz. So 1000 hertz that we can hear, right? Acoustic frequency is almost zero frequency to 20k hertz. So if we increase this, it's a higher frequency than previous, right? And also, see there is a sine waves. Originally, if you drop this to 0, what happens? If you 1 hertz, there's no 0 hertz. Then that is this. This is 1 hertz, red. So blue line is the reference signals. So compare this reference signal. If we increase this, say, oh, didn't. Look at that red line. Same magnitude, same amplitude, right? But only difference is the wavelength. Therefore, we have different hertz. And depending upon, I mean, as the frequency increases, we can hear the different pitch, different tone of sound. But this program doesn't generate over 20k. If it's over 20k, then I can test, for example, if we have somebody who can hear more than anyone else, like doggies, similar to doggies. If I put here 1000. If we have some decibel, that's only magnitude, a little bit of magnitude decibel. Only this. Oh, should be more than this, right? You want the magnitude? I mean, okay, let me stop this. Okay, let me close this. Only why we look at this, there's a sine wave. Um, so, so we can see um, we can increase the amplitude, we can increase the frequencies, right? Increase the frequencies. We have four chart here. This is given A. So amplitude 1, frequency 1, 0 hertz. Oh no, not 0 hertz. Phase 0, which means there is no shift. Therefore, period is still 1. That is this. If this is given, if we say, hey, let me decrease the amplitude by half, like this, then signal becomes like this. This is exactly half, right? Half the amplitude from here there. So this is B. C, we can increase the frequency, double, from 1 to 2, which is period is from here there, right? Now period is shorter. From here there, double, right? Twice. I mean shorter. Half the size of period, therefore double frequencies. For the same length, there is a 2 repetitions, 2 cycles. In this case, only 1 cycle. We can think of phase shift. Pi is 180, right? 180 divided by 4, then 45-degree difference. If we put this here, then it shift earlier. So it's supposed to start from this early, but our concern is from this point. So signal is like this. It turns out that there's a shifted. Okay. A little bit of basic. So they're all in time domain. Time domain. If we see this signal in time domain, then we can see, oh, there is 2 frequencies within this unit time, for example. Then that frequency occurs that many times. We can depict that way. This frequency, let's say frequency f, if this is 2, then 2 occurs how many times? Maybe 2 times or 3 times, or some amplitude. In this case, frequency appears this high. In this case, 2 different frequencies appear. So we have 2 points in this frequency axis. This whole, the left side, is depicted over time. But right hand side, they are depicted over the frequency. What it does here is that, let's say this is frequency is f, This frequency is 3Fs, right? Then, by the way, this third one is the combination of this. We'll look at that in the later slide. If we add this and that, then the signal looks like this. Therefore, if we interpret this time domain signal in frequency, then in the frequency domain, we might have this. So addition of these two signals in time domain is this. This is addition, right? Addition in time domain. Addition in frequency domain is this. If you look at these two different analysis, let's say I want to analyze signals in time domain. By looking at the third time domain frequency, the waves, then we can see, oh, yeah, that's really the combination of the top one and the middle one. Can you imagine that, right? If you look at the right hand side, third one, this is uh, the frequency domain pictorial explanation of the combined signal. But this combined signal in frequency domain can tell us very clearly, very clearly, which we cannot see in the time domain, but here, all is a combination of two different frequencies. Right? Two different frequencies, one F, the other 3F. Right? So, for some analysis, we may need to use frequency domain analysis. For some others, this doesn't tell us the shape, right? By looking at this frequency domain analysis, we cannot tell that how does it look like. Is it really a digital signal or some analog signals? We cannot know here. That can tell only from this time domain, right? In time domain, we clearly see, oh, there is analog shape like that. But if we analyze the signals in both ways, then clearly it is right? In time domain, oh, yes, that's interesting. Oh, yeah. So, signals used to be converted from left to right to left. They are correlated. Not just correlated, press currents. Clear. So there's FT form available. We don't have it, right? There's only electrical engineers who do. They did that for many years in that used to do it. Did you do it? Creative transformism, DFT, FFT. Now MATLAB has a very powerful tool to convert. So for example, if we have this kind of time domain signals, then which is clearly see in frequency domain like that. Right? Whatever that is, can be converted. So what happens? This is same as before, frequency. This is, let's say this is some reference wave and we have another wave, we can add them, this and this, together.
The way signals are added and combined, we can add data over carrier signal. Right? That's what we have to do. We have a signal. I want to send this data over. So we can do that, right? Provided you can see here. Very, very clear. We can mix our hosts over telephone line with some signal, some power, to send some power. Signal over there. As long as the technology all and the other side, now, from our smartphone, we send our analog acoustic signal, and our phone generates signal, right? Cell signal is generated from your cell phone. So, in your device, mix them together and send out. When it is mixed, it's like this. Let's say this is carrier, this is data, mixed together. So signal that you can see from your cell phone is this. So the receiver side receives this and it's split. So if this is carrier, then carrier disappear. This is the data. So that you can hear. If it is digital, then you can see on your terminal if it is voice messages, then you can hear that also, right? So this is the mixing, multiplexing. So we use different terminology, usually addition, combination, mixing, now multiplexing, something. They're all similar ones. So if we do that more and more and more and more, we add, this may be added two signals. So more signal, more signal, more signal, more signal, signal. Digital communication. So finally, our digital communication is like this. This will be sent. So there is no noise, there is no interference. Clearly, can we see digital signals? So we split that multiple times. Oh, this is a voice message, this is an email, this is a text message, this is something. Okay. So, data versus a signal. Signal is a carrier, right? Like a vehicle, engine. Data is something meaningful that we want to achieve. Okay. So one example is LED signal and sonic protocols developed several decades ago, right? When Sony TV was invented remote. So we have device, remote controller devices like this, right? Like our cell phone right now. So that's one button. Preset mixer, signal mixer. And there is an LED light. LED light is a carrier. So pulse. That is light energy. Bio. Nothing. Bio is simply bio is bio. LED is the diode. Diode is simply in normal terminal for everyone. LED is light switch. On and off. On and off. Light on, off, on, off, on. Zero, zero, zero and one. Like a pulse. In theory, it's like this, right? Pulse generated. But we cannot see it. Why? So high frequency, we can see it if it is only 10 pulse per second, 10 times. Then we can recognize, right? We cannot even recognize 60 pulse. Can anyone see? Oh, it is 60 times per second. When you see the electric light bulb. If you see that, then your source is you're not eligible to take the course on this part. May go something. LED, what's the frequency? I think 45 or 100. Where is it? Oh yeah, 38. 38 kilohertz. 38 kilohertz. LED lights in 38 kilohertz. 38,000 fluctuations. So we don't know. If we look at that, then, for example, 5 pulse, I'm going to send one data. Another 5, I send another data, and something like this. So bit 0, 1, 2, 3, 4, 5, 6, bit 11. Yeah, somehow like this. So over the pulse, we can mix 0 and 1. Mixing is now understandable, right? As we look at mix is simply addition. One, another one. Addition means in device, okay, for one value, I can send 5 volts. If I have one more, 10 volts. If I have one more, 3 volts. So multiple them. So there's no code. Now we can practice. Or we do not. Right? But we have a lot of those. What do we know? So I have that. So I want Tech9. I can give it to you so that we can practice it. I have LED. If you have LED, you can bring it. If you do not have, you can buy it. If you pay 17 cents, then you will have one LED. Oh yeah, resistance, you can bring it somewhere. Yes. Without resistance, it should work also. If there is a resistance, that is accurate, more accurate. LED with Arduino, Uno, no problem. There's a code. We'll practice it. Tech9. So simply, this is Arduino. After this, we'll take a break.
this is Uno. Do you know Uno? Maybe online students may need to buy this. How much is this Arduino? Right now, I think about $25. You can find it from where? Amazon.com, right? Or Arduino. Or you can ask Pomelo to bring some from Italy. Oh yeah? Wow, that's a chip. Uh, so we have here uh, PWM pins. They're all PWM pins. PWM means P means pulse. W means width. Width. M means modulator.
So modulator, mixing, modulating, mixing, addition, combination, they're all talking about the same. Pulse width modulation
Pins being used. What it means is that this is a pulse. This is a pulse. Width can be
extended a little bit.
originally this is the width, but if it is 1, I'm going to modulate this. Therefore, width increased. By looking at this increment, we can say, oh, that is 1, number 1. That is number 1. All others 0. Some more modulation. There's a start.
So that we know this is a starting point. Okay. What was the movie? Which game? Some game. Photography movie. What's the title of the movie? It, War Games? Is it the game that just came out? Last year. Oh, that's 2014. Ender's Game? Huh? Ender's Game? No, not real game. Movie. I'm talking about a movie. That was World War II. Yeah. Yeah. Imitation. Thank you, Imitation. In the Imitation game. Well, everybody watches that movie? That is homework. There was some inaccuracies that he said. Right. What was the things that he found at the last one? Hitler, I believe, was what.
Yes. What is starting point?
They looked at. They developed a computer, first computer, like they know that, but they didn't know when there is always some signal that can tell us it's touching. What they figured out was that every message ends with exactly. Right. Exactly. And that is it. So by modulating with first with, this is a start. And then later is short, this is one, and then that's one, zero. What was the title of it? Imitation game. What did he imitate? Something fast, right? One lady. Oh, yeah. I forgot that. Can you explain? So does it imitate from the real world to apply to the signal analysis, right? As in, if you hear this lecture and listen to that movie, then you can understand. The only issue with it was like they portrayed him as somewhat like on the spectrum. The Asperger's, autistic spectrum, but he wasn't.
their life, so kind of was a little fake. I guess they're getting
Right, they developed some algorithm to decrypt, but only their problem is what's the point they can apply. Because there's time critical. They cannot do it all the time. There's always every morning there's some AM, I don't know what signals, what wavelength, what maybe AM or FM radio signals. So by listening that radio signals, they need to decrypt it, but they cannot read because it is continuous signals. But if they know this, then they apply immediately their algorithm so that they can.
Yeah, but they didn't know the machine was working until they got the stars. The machine was up and running, but they didn't know it was working before, and they couldn't get all the information. The way they portray Turing to someone in if he wasn't like the one that they just capture
So we may test it when it comes to this. Okay. Okay. So after this, we'll well, and also we not long ago, but we highly used the modem. Modem is still used, right? Modem. Why don't I have my? I need a pen. Okay, here. So modem. Actually, vice versa. Modem modulate digital signal to analog and analog signal to digital signal, right? So modem stands for MO for modulator, DEM for demodulator. So we all know that. And still in our network infrastructure, network configuration, we need to have many times a modem, right? We have a modem somewhere for that server. And there is a codec. Codec stands for codifier and decodifier, similar to modem. So it's analog signal to digital signal, but digital signal to analog signals. Very similar to this, but for different applications. Usually codec is doing for multimedia data. Modem is for network devices. And there's a digital transmitter. It transmits digital signal to digital. So now, having that said, we want to transmit data with no media. Then we need to generate a signal, right? What we need is that from the sender side, we send simply data. So receiver finally receive that data. Same thing. This guy send the data, and then receiver can receive the data, the exact same data that was originally sent out. So if we think of that, then telephone line is the analog data. Telephone line is a device that can take analog data to analog signals. Okay, we want to send the analog data over the analog signals. And also some other times we want to send the digital data over analog signals, analog data over digital signals, digital signal over digital data over digital signals. So 4 combinations possible, right? In every cases. If we want to use radio waves, then usually that is analog. So if we want to send the email, then there's a digital data. So digital data over the radio waves, so it can propagate. To do that, we need to think of we need to define some terms. First of all, data rate. Data rate is the rate at which data can be transmitted. The unit that we can use for data rate is usually bps. B for bit, not byte, per second, right? Higher frequency, then highly likely more bps. But depending upon the modulator techniques, right? Bandwidth. Bandwidth is the width. Bandwidth is width of the transmitted signals. So we call that hertz. And channel capacity is the maximum rate at which data can be transmitted. So depending upon the bandwidth, we have different channel capacity. This is a channel capacity. If we have a channel capacity, it doesn't mean that there is always the possible data rates. Data rates is more experimental measurement. Channel capacity is, there's a capacity. The amount of data to be transmitted is not the same as channel capacity, because channel capacity is a maximum rate, right? Sometimes we can mix use. In your first homework assignments, I was asking about data rate or channel capacity. So you can calculate that. There is a noisy also, and error rates. You can think of all of those. What is a channel in Wi-Fi, for example? Channel is over the spectrum of frequencies. If we are thinking of ISM band, then this is typical ISM. This is also 900 megahertz and a little bit over 5 gigahertz. If we consider the bandwidth where there is a 2.4 gigahertz frequency band, then there are about 14 channels, 14 possible channels. Each channel has 2,000 bandwidth. No, I'm sorry, it's not. What is it? Change this. 2,000, 2.423 minus 2.401. That is a bandwidth. That is a channel bandwidth. So this is the bandwidth, but we chopped that by allowing some overlap. This bandwidth, what is that? 2423 minus 2401, then 22 mega, right? 22 megahertz. Let's say 22 megahertz, that is the channel bandwidth. So we allocate channel bandwidth, channel 1, 2, 3, 4, channel 2, 14. There's some overlap. If you do not allow overlap, then you could use 3 on non-overlapped channels. So if you use a channel 1, but still more data to send or receive, then you can use channel 6 and channel 11, depending upon the way that you set. If you use channel 2, then if your system does not allow, because there is a possible interference, then you can use channel 7 and channel 12, something like that. Okay, that is a channel. So this is the bandwidth of a channel. What is the capacity? Your data, when you send the data, for example, in Wi-Fi, you are not going to use all the bandwidth, which means if you send high ether, then wasn't that what it was?
You probably shouldn't send 5 different
High mercy. High mercy, especially on this online. I want to put this on YouTube. Right. Yeah, high mercy. So if we send a high mercy, then high H. H can be the character H, data H should be mixed with all the bits or bytes in this, all throughout all the bandwidth. We don't do that, right? It's a lot of ways, right? So right now we have 22 megahertz chop. So you use one channel. Even in one channel, we're not going to occupy that channel throughout all the time. Still, we can mix it with other data, right? For one channel, we can share that channel with 100 people, 100 different messages. Still possible, right? We can divide by time, divide by frequency, and time sharing, frequency sharing, things like that. But anyway, that is a channel capacity. For channel capacity, we need to consider 2 things: sampling rate and noise. And therefore, Nyquist developed a formula so that we can estimate data rates. If we have some, let's say, this bandwidth, then what is the data rate? Or channel capacity. As I said, the data rate is more experimental measurement. Channel capacity is more theory, therefore that is the maximum. In the homework assignments, I wanted to calculate channel capacity. What is the maximum data rate that it can utilize? If you consider noise, then that much smaller amount of data can be transmitted, right?
So if you use noisy, then you might have different data rates. By considering this ratio, signal to noise ratio, that is developed by Shannon, Cloud Shannon. Shannon, David, what countries? What is his heritage? Okay, I don't know. Nyquist, what about Nyquist? Nyquist. Oh, is that right? To me, that is called uh, like aspirin. For sampling rates, multi-level is useful. What is the level in wireless communication? And that's right. When the device generates signals, it doesn't generate only 5 volts signals, 0 or 5. It can generate depending on the message, 5 volts, 10 volts, 15 volts, 10 volts, 25 volts. And there is multi-level. If we have multi-levels, then what happens? Do we have more data to sample or less data to sample? So in the next slide, so level is that. If we have two level, then 1 or 0. If we have a multi-level, then 0, 1, 0, 0, 0, 1, 1, 0, 1, 1. If we have more, then 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, so more and more. Right? If you have only two level, then if you have no level, then what happens? Only one, right? But usually we have levels because device needs to may be able to send power or no power, or positive power or negative power. So always dual. Start from dual. So power over 2. So level 2, 2 levels, 4 levels, 8 levels, 2 to the power 3, 2 to the power 4, then 16 levels, 32 levels, 64 levels, something like that. So it is always log-based 2. So Nyquist theorem explains like that. Firstly, given a bandwidth of B, the highest signal transmission rate is 2B. Why 2? Bandwidth. So there's a hertz, right? 1,000 times fluctuation. That at first, how many data can you send? 1,000 data sets, right? For each cycle, you put 1 data. In theory, but that is maximum. No more than that, right? And again, if there's 2 levels, so on and off, then it is on, then 1 data, off, another data. Therefore, double, right? Frequency times 2. That is the maximum. That is a specific channel maximum. But in real, of course, a lot more than it, right? So for example, we have an example. So you can follow this example. with the multi-level, if there is a 2 level, then apply that. If you have 3.4 hertz, I mean 3,500 hertz band, frequencies, then the maximum capacity, ideal and maximum, then that is 7,000 bps, bit per second. Multi-levels. Then this is 2 level times low 2 base and m is the multi-level. If it is 2, then low base 2 will be 1. That is that, right? If it is 4 level, then 4, right? 4 levels, then double. 8 levels, triple. Signal level is 8, then what is maximum data rate? Maximum data rate is nothing but channel capacity. What is it? 3,500 times 2. Level 8. This times 2 times 3, so times 6, so 6 times 35, then probably somebody said that, right? That is. But in this case, we never take the noise into consideration. There may be some noise. Not all the data that we could send. Part of that is noise. Just this. That's not the data. That much reduced, right? So, to do that, we need to first take a look at noise. We can think of have different definition of noise, right? Here we look at signal to noise, or data to noise, signal to noise. So compare the signal and noise, data noise. We call them SNR, signal to noise ratio. Usually, look at the power, signal power and noise power. Device generates different power to send the data. Maybe the noise comes from device itself, then it's from power. Maybe for any reason, by different types of multiplexing, different levels, different power. But anyway, the ratio. So SNR is nothing but ratio. So this portion is ratio, SNR. But when we compare this, when we convert this to decibel, you heard of decibel, right? Noise decibel. If it is higher decibel, noisy decibel, then more noisy. Decibel is not only the term to be applied to noise, but in this case, noise. It's always a ratio. Ratio applied to the load base 10, and times 10 for this signal to noise ratio. So 40 decibel, then we know how it is, how much it is, right? Usually, on
common conversation. Recording to 660. But anyway, so Shannon formula gives us B, that is the frequency, log base 2, 1 plus SNR, signal to noise ratio. So in practice, this channel capacity will be lower than Nyquist channel capacity. Nyquist is so optimistic. It doesn't mean that Shannon's theory is pessimistic. It's not yet pessimistic. But pessimistic, if I would say, zero.
Formula assumes white noise, thermal noise, heating, therefore impulse noise is not counted for, attenuation, distortions, all kinds of noises that affects that. So in this case, phone communication, assume that phone wire bandwidth is 3500 hertz and SNR is 30 decibel. What is the channel capacity? We need to apply that, right? This form. Solution is next. So SNR is 30 decibel. See, look at here. This is a decibel. Decibel. The one that we want, this is not in decibel. That's what I say here, right? SNR is not in decibel. So what should we do? SNR is only this portion. Entire this is 30. That's what it means. So from this formula, we need to calculate this term only. So from here, SNR, signal to noise ratio, is 1000. You need to calculate this, right? Anybody doesn't know how to calculate? Everybody knows that, right? We divide that by 10, 10 here, 10 here. We cancel this out. And 30 over 10, then there is a 3, right? So log 10 based SNR, this is what we want. We don't have to worry about that. I want this 3. According to some formula, from here, this can be obtained 10 to the power 3. 3 comes here, 10 comes here. So 10 to the power 3, which is 1000. So now capacity is, according to that, this is frequency times log 2, 1 plus this. Therefore 35 k bps. What does that mean? 35 k bps. Compare this to previous. This times 6. What happens? Right? 21k. 21k bps. Oh, wait a minute. Oh, this is, how come this is more than that? Oh, well, actually this is more than that. because this, oh yeah, 21K. Huh. I don't know. I mean, in this particular case, we cannot say that, right? But anyway, this is homework one. I want you to practice in this way. Okay. So we know, given frequency bandwidth, for example, ISM band, industrial, scientific, medical band, then we can, if we usually we use a 22 megahertz channel bandwidth, then 14 channels. So for each channel, we can modulate with data sets. But it doesn't mean that any data can continually use that channel at all. So it can be shared with other data sets as well, right? So it turns out that a lot of data streams can be transmitted. Transmission medium is physical path between transmitter and receiver. Usually in our, well, this is general term. So there is a guided media. For example, wired communication, then copper twist pair, coaxial, optical fiber, and so on and so forth. They're all guided media. But in wireless, there's no such media exist, but unguided. Therefore, that is wireless communication. The media is nothing. It depends. Yeah, there's air, right? Air. If there is no air, what happens? High speed or low speed? High speed, because there is no resistance. Right? Therefore, we can receive data from later further away. Air only in surrounding the Earth, right? This globe. There's no air in other stuff, right? Oh, you don't know? You've never been there? Me neither, right? General frequency range, microwave frequency range is 1 gigahertz to 40 gigahertz. Directional beam possible, suitable for long distance point-to-point transmission, used for satellite communication. So satellite communication in this microwave communication, right? So that frequencies, if it hits the meat, then meat can be burned, right? If we put if you put your hand in your microwave device, close, start button, then it will burn, right? Have you tried? You cannot try, right? Because you cannot close the door. Would you be able to try and tell me next week? So that frequencies meets the meat, then there's a heat. There's a heat because of that frequencies, right? Radio frequency little lower than this microwave. 30 megahertz to 1 gigahertz. So radio frequencies. Our cell phones and Wi-Fi's mixed use somewhere here. So we call that 2.4 gigahertz. Infrared, higher frequencies. Infrared. If you use infrared. Many sensors. There's IR sensors, infrared sensors. So it generates higher frequencies. I think multiplexing technique. What happens here is that this is a channel, right? So you send, for example, your signal, your digital signal is like this. This is your digital signal, but you mixed with this your data. So mixed this with that. This is your data. Your data will be used, for example, this much can be represented these two data sets. So multiple times it appears. And next, the next length, this much will be mixed with that signals, that carrier, and all the way up. You might have a lot more than this. This is one single data. You have another sets of data. So many different sets of data can be multiplexed with this given signals. There are two ways of those. Time division multiplexing and frequency division multiplexing. You can divide in time, which means frequency you can see simply, right? Here, okay, I want to use this frequency, my data, at time t1, this frequency, your data, that frequency, her data, and things like that. We divide the frequency. Another way that you could do is, in this picture, there's no timeline, right? That goes at time t1, and next time, and next time, and next time. So at this time, I'm going to use my data, whole bandwidth. Next time t1, okay, now your turn, your data. But at that time, at each time, we can use only this much. At time t1, I'm using entire, but only that. At time t2, okay, your turn. So you can use that much data. At time t3, okay, you can use this. Time t4, hey, now it's my turn. Time t5, okay, her turn. Time t6, okay, your turn. Things like that, right? That's possible. That is this. Time division, multiplexing, and frequency division multiplexing. We can combine them together also, time and frequency. In addition to this, we can do also code division multiplexing, so-called CDMA. What does that mean is, I'm going to use this code. I'm going to use this. This is actually code. Okay, so I'm going to use that. For example, oh, instead of using this whole, I am going to divide this code. Usually, I need to use all this code for carrying out one data. But now, CDMA, that code can be divided so that we can carry more. As the way that we can, in order to carry more, we divide the frequency, we divide the time. Similarly, we divide the code. Okay, so that'll be next time. Any question?
Can you go back to the formulas, the homework?
This is in the slide, the blackboard.
Or is it- okay. But, we're using, we're using that formula right there? C equals 2B log 2.
You use this, use that. 2. If there is no question, then I will turn off this. Have a good night.